Hello friends, in this video we are going to discuss about nerve impulse conduction along the length of the nerve fiber. We must be aware of the general structure of the neuron or the nerve fiber, that it has dendrite, cyton and axon. The nerve impulse which is conducted along the length of the nerve fiber travels only from dendrite to cyton to axon in one direction, that is, it has a unidirectional flow. The information flows in a particular format, like we say the waves have a format of traveling, the computer information has a format of traveling. Likewise, the information that travels in our body along the length of the nerve fiber also has a pattern. That pattern is with the help of difference in the ionic potential in the form of an electrical signal. That when there is a difference in the charges inside and outside the nerve fiber, that difference in charges leads to the production of an electric current type of an impulse, and that flow of current along the length of the nerve fiber is known as nerve impulse conduction. In true sense, it is not a current, but it is similar to a wave of a current that is produced by flow of electrons. Here that wave of current is produced because of flow of ions. It is not the subatomic particle which is moving, it is actually the ion which is moving across the nerve membrane that is producing a potential difference, because of which there is a difference in charges, and that difference in charges leads to the flow of charges in the form of ions, right? And that flow of charges is known as an electrical impulse. We need to understand how is that flow of charge created, what is responsible for the flow of charge, and for how much time does it flow, what change does it bring about in a nerve impulse for its travel from one point to the other point. To begin with, we need to know what is the initial starting status of the nerve fiber before it is activated, and we call that initial default status of the nerve fiber as the resting nerve fiber. And since we are talking of the conduction of nerve impulse which happens along the length across the membrane, so we talk about the status of the nerve membrane, that if I have a nerve cell, that is a neuron which is also known as a nerve fiber, the nerve fiber membrane outside scenario and inside scenario should be clear to us. The outside scenario is known as the extracellular fluid, the inside scenario is known as the intracellular fluid. For example, if this is the membrane of the axon, I am just drawing a small section of the axon, this is the axoplasm, that is the membrane of the axon, also known as axolemma. The fluid which is present inside the nerve fiber is known as the intracellular fluid. The fluid which is present outside is known as the extracellular fluid. We need to know what is the ionic concentration in the extracellular and the intracellular fluid to comment what would be a change in this scenario. I say today I am 80 kgs. Okay. What if in later years I become 100 kgs? So I have gained 20 kgs relative to what you saw 20 years or 10 years back. So if you do not know the 80 kg value, you cannot comment that if a person is 100 kg, has the person gained or lost weight. So you need to know the initial status to comment on the final status. Likewise, we need to know the initial status of the nerve cell or the fiber or the neuron to comment when it is activated and when it is conducting the nerve impulse. And that initial status, we basically focus on the ionic concentration of the intracellular and the extracellular fluid, and this concentration defines what is going to be the potential of this nerve membrane. जैसा ionic concentration होगा वैसा ही उसका potential होगा, right? And we observe that the ionic concentration of the intracellular fluid has a high concentration of potassium and chloride and a relatively low concentration of sodium, which we represent as this, that at rest a nerve membrane has a high potassium inside, low sodium inside and a high chloride inside. Now, outside, relatively, potassium is low in amount, sodium is more in amount. Chloride we do not talk about in the extracellular fluid because chloride is relatively immobile. It doesn't move much. So the concentration is very incipient outside. We do not comment about it. So it's a high concentration inside only, producing a negative charge inside. Also, we say that we must know the concentration gradient of both the movable ions, that is sodium and potassium. Since sodium is more outside, less inside, it has a potential of outside being more, and we know that ions diffuse from a higher potential to a lower potential, so its gradient is towards inside. Likewise, if I comment on the potential of potassium, it is more inside, less outside, so it has a gradient from a higher potential to a lower potential in an outward direction. So if we will comment on the movement of ions through the diffusion channels which do not require any energy, the sodium is ideally going to flow inside and potassium will flow outside. Always, if there is any movement of ions of sodium or potassium, they are going to move along the concentration gradient through diffusion channels. Then the movement of sodium is going to be inside and the movement of potassium is going to be outside, right? What if it is not a diffusion ion channel? It is an active potential movement through the ion channel. That means we are going to use energy and pump the ions against the concentration gradient. उसके लिए भी concentration gradient मालूम होना चाहिए कि सोडियम का inside है, अगर against move करेंगे तो सोडियम outside जाएगा. Likewise, potassium का gradient outside है, against the concentration gradient move करेंगे तो inside आएगा, right? And with such an explanation, we can understand the working of a sodium-potassium active pump which is present over the nerve membrane. This sodium-potassium active pump, as observed, works on the nerve membrane such that it pumps the sodium and potassium ions against their concentration gradient. Sodium ka concentration gradient, movement of sodium inside, so it's going to move against, outside. Potassium ka concentration gradient moves the potassium outside, but against the concentration it's going to move inside. And when it moves the sodium and potassium, it moves in such a number that more potassium is pumped outside, sodium is pumped outside, and less potassium is pumped inside. So relatively, outside has a higher positive side, inside has a lower positive side, which makes the nerve membrane polarized in such a way that outside the nerve membrane the charges are positive and inside the nerve membrane the charges are negative. Had it been this sodium potassium channel not working, then the ions would have moved across the membrane through diffusion channels to make the polarity zero. The ions would move and they will balance each other's charges and the resting membrane would have a zero potential. But it's not like that. The ions do not move just through the diffusion channels. They have an active pump which maintains that the potential does not become zero. There is a difference from outside and inside, which makes the nerve at a rest and which gives the property to the nerve that the resting nerve is polarized. Polarized means that it has a charge. It's not neutral, it's not zero. The outside and the inside ions do not balance each other. There is a slight imbalance that keeps nerve inside to a bit negatively charged potential and outside to a bit positively charged potential. As we've written it here, that the resting membrane potential is minus 70 millipole. Minus means that it possesses a charge, a negative charge. That's why we call it polarized. And this polarization of the resting nerve membrane is due to two main factors. One, obviously the sodium potassium pump, which is acting against the concentration gradient so that there is no balance. Second, the differential permeability of sodium and potassium. See, potassium is relatively less permeable to go on the outside and vice versa for sodium. So because of it, the concentration of the potassium becomes more inside and concentration of sodium becomes more outside. And chloride is very immovable, so it becomes more concentrated inside. So this differential movement from out to in and in to out creates a more negative potential inside the nerve. contributing to the negative membrane potential of a resting nerve cell. Now in this situation, when I have a polarized nerve, this polarized nerve is at rest. It's an observed science. When I have observed a nerve cell at rest, it has a negative potential. Now if I have to activate it, I have to change this polarity. नहीं तो ये रेस्ट पे ही रहेगा. Ideal default situation is that it is negatively charged. If it has to get activated, that means it has to change from rest to action. It has to change its polarity also. It should change from minus to either 0 or minus to plus. Then only I can say कि हाँ, now there is a change from previous situation. Now it is not at rest, it is at some other condition. The other condition that it is active. Now what is responsible for that activation of the nerve? Just like we have the Newton's first law of motion, that anything remains at rest until unless an external force is applied, the law of inertia which we say. So likewise, even my particular nerve membrane remains at rest until unless an external force is applied or an external stimulus is applied. That external stimulus is for the nerve membrane, can be from inside the body or outside the body, right? Once that stimulus is applied, it would have some potential. The potential we measure in volts. So we say it would have some minimum voltage which would actually act on the nerve fiber. Now, this voltage affects what structure on the nerve membrane? The voltage affects the voltage gated ion channels. एक बाहर से जो फोर्स लगाई, उस फोर्स में एक पोटेंशियल था, पोटेंशियल को हम वोल्टेज में मेजर करते हैं, तो ये वोल्टेज किसको इफेक्ट करेगी, है ना? क्या फर्क पड़ेगा इस वोल्टेज के अप्लाई करने का? दिस वोल्टेज विल अफेक्ट द वोल्टेज गेटेड आयन चैनल्स, द प्रोटीन चैनल्स which are present on the nerve membrane, structure of nerve membrane, if you can recollect. So we have certain voltage gated ion channels present on the nerve membrane which allow the movement of ions along the concentration gradient. Against नहीं move करते, वो बस बंद रहते हैं. खुलते तब है जब बाहर से कोई मैसेज आता है या वोल्टेज आती है कि अच्छा खुल जाओ. तो जब वो खुल जाएंगे, मूवमेंट किस डायरेक्शन में होगी? अलोंग द कंसंट्रेशन ग्रेडियंट. ठीक है. सो व्हेन माय नर्व इज एट रेस्ट, दीज वोल्टेज गेटेड आयन चैनल्स आर क्लोज्ड. They will only open when there is an external force or a voltage applied, a potential applied. And that minimum potential which can activate a voltage gated ion channel and open it is known as the threshold stimulus or the threshold voltage or the threshold potential. That this is an external stimulus which has a minimum potential to open the voltage gated ion channels. That's why the stimulus is known as the threshold stimulus. Okay. Once there is a threshold stimulus, it has a certain value. It should be some 10 to 20 millivolts less than the resting membrane potential. That means it should be something about plus 10 or plus 20 millivolts that can change the resting nerve membrane potential to minus 70 to minus 50. Minus 70 plus 20 millivolts is equal to minus 50 millivolt. As the nerve membrane changes from minus 70 to minus 50, the voltage gated ion channels open. Okay, voltage में change आया, बाहर से voltage आई, खुल जाते हैं. ठीक है. So once it receives the threshold stimulus, then only it opens. 20 से कम में open नहीं होगा. 20 से ज़्यादा में ऐसा नहीं कि ज़्यादा देर के लिए open होगा. The time is fixed that it is going to be open for 0.1 millisecond on 20. If it is 30, 40, 50, it won't make the difference on the time. It is like following all or none principle. Either open or close. Doesn't matter. कितना voltage लगा दो, या तो खुलेगा या तो बंद रहेगा. इससे कम पे खुलेगा नहीं, इससे ज़्यादा पे इतनी देर के लिए खुलेगा, चाहे कितना ही ज़्यादा लगा दो. We call it the all or none principle followed by the nerve membrane. Though, if I apply a continuous, simultaneous stimulus, I applied a stimulus of 5. Then next second another 5, then next second another 5, then next second another 5. If it is simultaneous, consecutive, then these stimuli may add up, become a plus 20 millivolt stimulus and lead to a summation effect, becoming the threshold stimulus and activating the voltage gated ion channels. But if it is not continuous or simultaneous or consecutive, then it won't be. Then only all or none principle. If there is only one potential and if it is less than threshold, it will not open the voltage gated ion channels. I hope it's clear. Moving forward, once the voltage gated ion channels open, we need to decide which one open. So upon the threshold stimulus, the sodium voltage gated ion channels open. And when they open, what is the direction of movement? Along the concentration gradient. Initially we have studied what is the concentration gradient of sodium. It is going to move the ions inside. So upon the threshold stimulus, the sodium gated ion channels open and the sodium, the positively charged sodium, moves inside. The positively charged sodium is going to move inside. If 3 of them move inside, it is going to neutralize the 3 negative ions which are present inside, and it is going to become 0. That means the negatively charged nerve membrane, which was minus, has now turned to 0. This effect is known as, from polarized state, it is becoming depolarized, right? And this depolarization actually activates the nerve fiber. And since the sodium gated ion channels are open for 0.1 second, or which we could say the 1 millisecond, the entry of sodium is continuous. First, it is going to lead to depolarization, and a further entry of sodium is going to make the nerve membrane positive in its potential, such that relatively the outside becomes negative. So once the sodium is flowing inside and making the nerve membrane potential, there comes a maximum point after which the sodium channels close, and post that there is no entry of sodium, there is no more positive charge which is going to enter, and the positive potential becomes static. Okay, this is the maximum positive potential which the nerve membrane can gain post the opening of sodium ion channels for 1 millisecond. You understand? Now, this potential, the maximum potential, is known as the spike potential. At this spike potential, if you observe, the nerve membrane creates 2 zones. One, a positive zone on the inside, the other, the negative zone on the inside. We label them as 2 points, like 2 adjacent points, point A, point B. Now point B has a positive potential, point B has a negative potential. And in these 2 points, I observe a potential difference. Whenever there is a potential difference, it creates a motive force. You know, we say a proton motive force or an electron motive force, a charge related difference of force. Because of this difference in potential inside the nerve membrane, because of an excess positive, there is flow of ions. And this flow of ions needs to complete the circuit on the outside also. So there is a flow of ions on the outside also. The outside is relatively negative at the A point, relatively positive at the B point. So if the ions are flowing from B to A inside, they are going to flow in the opposite direction on the outside to complete the circuit, which we say the conduction and convection. The circuit should be complete. And once the circuit is complete, it reverses the polarity at A point and B point. If you can see, now the A point becomes negative inside, which was positive earlier, and positive outside, which was negative earlier, regaining your resting membrane ideal situation. But the point B has now become positive and outside relatively negative. And when I compare point B to the adjacent point, which can be point C now, I observe now they have a potential difference. Again the charges will flow. At point C, when the polarity will change, it will have a potential difference with point D, and this wave continues until it reaches the terminal nerve ending. So we say that because of this spike potential, there is a creation of potential difference which leads to the conduction of nerve impulse from one point to the other point. Thus, this spike potential is known as the action potential, which actually brings into the action of conduction of nerve impulse from one point to the other point. There is a hitch in this. Why don't we just consider the flow of ions inside? But if there is going to be just flow of ions inside, it will not be able to complete the circuit. If there is no ions flowing outside, then the inside will become negative, the outside will also remain negative. There is no difference in the permeability of ions, or there is no difference in the potential, which disobeys the first situation, that there is differential permeability and concentration of ions across the nerve membrane. So if there is no difference, there will be no movement, there will be no conduction. Hence it is important that the outside circuit should also be complete for maintaining the default nerve membrane condition. Clear? Now how this is going to continue till the nerve ending? How does it stop? Will the nerve ever come to rest? Yes, it stops. Once the sodium ion channels close and this action potential is generated, the potassium ion channels open. And we know that when the potassium ion channels will open, again the movement of ions will be in the direction of the concentration gradient. And what is the direction of the concentration gradient of potassium? It's outside. So as soon as the potassium ion channels open, it leads to the movement of the positive charge which is present inside to outside. And when the positive moves outside, the negative charge is regained inside the nerve membrane, leading to the regaining of the minus 70 millivolt of the resting nerve membrane. Now at this position, both the sodium and the potassium ion channels are closed. Only the sodium potassium active pump is active, which maintains the resting nerve membrane potential to minus 70 millivolt. So now the nerve membrane is again ready to receive another stimulus and get activated. So a nerve does not conduct another impulse until it regains its resting nerve membrane potential. Then again it's going to remain in the excited state only forever, and it will not take another nerve impulse. So for the nerve impulse, new nerve impulse to be generated, the nerve has to come back to the resting membrane potential, which is gained by opening of the potassium ion channels and movement of the ions outside, so that now from the depolarized state it again comes to the polarized state which it was, and this process is thus known as repolarization. Clear? We can conclude this, that whenever the closure of sodium ion channels happen, the voltage gated ion channels of potassium open and there is exit of potassium regaining the resting membrane potential. Whenever this repolarization is happening, again inertia of movement, the ions move more outside and the inside of the nerve membrane becomes more negative. है ना? That more negative potential is known as hyperpolarization. कि repolarize तो हो रहा है, कुछ ज़्यादा ही repolarize हो रहा है, hyperpolarize हो गया. So it takes a bit of time to come back कि minus 70 से minus 90, minus 100 millivolt हो गया. But we want the nerve membrane to become minus 70 only, which is maintained by active sodium potassium pump, and it gets it back to minus 70. Minus 90 से minus 70 आने में कुछ time लगेगा. That time period is known as the refractory period for the membrane to gain its resting nerve membrane potential. We can draw a relative difference in the potential of the nerve membrane with respect to time. Says that the time is on the x-axis, the potential is on the y-axis. This is the positive potential, this is the negative potential, the positive y or the negative y, right? If I conclude at time t is equal to 0, when the nerve is at rest, the resting nerve membrane potential is minus 70 millivolt. ठीक? Till some time it remains at rest. Now once there is an external stimuli which is applied, which I call the threshold stimulus. It opens the sodium gated ion channels and there is entry of positive charge. So that entry of positive charge changes the potential from minus to 0. And since it's an inertia, it's going to remain open for 0.1 millisecond. 1 millisecond. So it's going to keep increasing the potential. This is 1 unit. This is 1 unit of time. So we say because of the opening of the sodium gated ion channels, there is a change in the potential of the nerve membrane from -70 to 0 and from 0 to a highest positive potential, say for about plus 30 millivolt. This changing in the potential is known as depolarization, and attainment of the maximum potential. The maximum potential is known as the spike potential or the action potential. At this, the sodium ion channels close. Once the actin potential is gained, the sodium channels close. What opens? The potassium channel opens. And now the potassium channels are going to lead to movement of positive charge outside. So the positive of the potential of the nerve membrane will decrease. So now again the positive potential will start decreasing. Once it starts decreasing, it decreases below the point of -70 millivolt. You understand? Why? Because of the inertia of the movement of ions outside. This process of changing the potential from positive to negative is known as repolarization. This repolarization is achieved due to opening of potassium ion channels. The movement of sodium ion channels led to entry of sodium, therefore increase in the positive charge, whereas opening of the potassium ion channels will lead to exit of potassium and lead to a change from positive charge to negative charge. But this negative charge becomes way negative the resting nerve membrane potential. And thus we say it is becoming hyper negative. The polarization is becoming hyper, and we call this particular change in the potential as hyperpolarization. Clear? So this hyperpolarized nerve has to come back to the resting nerve membrane potential, so that the nerve can again be in a situation to get activated and conduct a new nerve impulse. Until it comes back to its resting nerve membrane potential, it will not be able to conduct a new impulse. Hence, the time period which it takes from a hyperpolarized state to a resting nerve membrane potential, time is on the x-axis. So this time period which it takes from point where it is hyperpolarized, say this point, to the point it gains back its resting membrane potential. This time period is known as the refractory period. Refractory period. Understood? So this is all about conduction of nerve impulse along the nerve fiber. It starts from the trigger point, which are usually situated at the dendrite. From dendrite it travels to the cyton, from cyton to axon, and from axon till the terminal nerve ending. When it reaches the terminal nerve ending, it activates the synaptic vesicles to fuse with the presynaptic membrane and release the neurotransmitter across the synapse. Okay, so I hope it's clear to you, and we're going to be seeing you very soon with more videos and understand the concepts of biology. Thank you very much.